All right, I think we were right here. So we're going to do electron configuration and move pretty quickly through that. And then we'll talk about periodic table trends. All right, so electrons are arranged in the atom in a series of levels and sublevels. So levels are going to be our energy levels. So those are like 1, 2, 3. So that's kind of how far out they are from the nucleus. Sorry, sometimes I get a little bit of duplication here. How far they are from the nucleus. So as N increases, then they become higher in energy, larger orbitals, farther from the nucleus, and they can hold an increasing number of electrons. So if you do not need to draw this. So like in the old-fashioned way, where you just scientists just thought the energy levels kind of, or electrons were kind of like the planets going around the sun. Those would be your energy levels. So the closer they are to the nucleus, and lower they are in energy, and then they're going to get larger as they go out and higher in energy. And because of that, that's why the electrons will come and feel closest to the nucleus first. Because remember, everything wants to be at as low of an energy level as possible. Also remember that your energy levels, they're not always in the same period as the element. I'm gonna hit something that's making me erase everything. Always the same as element. So what I mean by that is flip flop between these two. If I can find it. Ooh, there we go. So this is your little periodic table using your different sublevels. But if you remember from Chem 1, like for instance, iron, it may be in period 4. I mean, I'm sorry, it may be, yeah, period 4, but it fills in a period, it fills in energy level 3. Y'all remember that from Chem 1? Your S, they are always in the same period as the element is in. And don't forget, this is S over here too. Same thing with your P's. But then it starts changing. Your D's are always one behind what period they're in. So now that I've written all over this, but that's your 3D, even though it's in period 4. And then your F's, which kind of fit right down in there, those are 2 behind the period that they're in. And remember, this periodic table here is just a tool to help you with the order of filling. So that means that electrons will go into a 4s, even though it's a higher energy level, it's actually a little closer to the nucleus. So they will fill a 4s before they will start filling a 3D. So this is just a tool to help you with that filling process, or the order that which they fill. All right. So the next thing that we have is we have our energy level, we have our main energy level, and then we have our energy sub levels. So this is where we did our S, P, D, and F. So our S's, they're spherical shape. They only have 1 orbital and they'll hold 2 electrons. So when we were doing those and drawing them, it would always just be one line because the line represented the orbital. And then if you remember, when you fill them up with the electrons, the arrows represent the electrons, and one is going up and one is going down, because that's how they exist in opposite spins, because it decreases the repulsion some. Then the P's have 3 orbitals, so they can hold 6 electrons, because each orbital can hold 2 electrons. Also, if you remember, and we'll talk about this rule in a little bit, the way that they feel is 1 in each orbital before they start doubling up. Same thing, they're trying to get as far apart as possible. So that helps a little bit with that. 5 orbitals for the D sublevel. So you may not feel the need to draw these lines, which I perfectly understand. I'm just taking it from the beginning. And then the F's have 7 orbitals, so 14 electrons. 5, 6, 7. And once again, if you count across an F, you'll count 14 boxes, because each box represents an electron. So S's are spherical shape, the P's are dumbbell shaped, and then they start getting more complicated. And remember, it's not like the planets going around the sun. These are 3D areas. They're those blue over there. Those are supposed to represent some of the different ones, and they're kind of built on top of each other. Like I like to think of like a clown that can do a balloon and like put a balloon inside a balloon. It's that kind of situation. And remember, these are areas of probability of where the electron exists, that we don't really seem to know exactly where they exist at one time. Quantum numbers, we're going to talk about quantum numbers more than we talked about it in Chem 1, but y'all do not actually have to know how to give an electron a quantum number for AP tests. You might have to do that if you take it in college. So the quantum number is the address of the electron, and there are 4 quantum numbers to describe an electron. So 1 electron in an element. No 2 electrons in an element can have the same set. So every electron in the element can be assigned a set of 4 quantum numbers, and then none of those will be duplicated. The first 3 will get down to 2 electrons, and then the 4th one will separate that down into where only 1 electron will have that number. So it's kind of like if you go to the Astros, you go to NRG, and then you find your section, and then you find your row, and then finally you find your seat. And hopefully nobody should be sitting on top of you in your seat. Same thing here. Once we finally get down to the seat, then it's going to separate it out. So our first one is your principal quantum number. And that is the energy level, represented by N. That was probably the easiest one to understand. The next one is your angular momentum quantum number. So that's your second one. It's represented by an L. And it has values from 0 to N-1. And this is where we talk about the SPD and F in this. So we use SPD and F in electron configuration, but you don't use those letters whenever you're talking about quantum number. They have a number that's actually assigned to that. So that second quantum number, the angular momentum, talks about the shape of the orbitals. So that corresponds to the sublevels. So 0 is the number that's assigned to an S orbital. And same thing as far as, how many orbitals and how many they can hold, like we already talked about. One is the quantum number that is assigned to P or P sublevels. D sublevels have been assigned a quantum number of 2, and F sublevel, all F sublevels have a quantum number of 4. So the next one is your magnetic quantum number, represented by M, and then that's a little cursive L. At this point, you will have 2 electrons in the same, or in the element. That will have the first 3. I'm just going to put Q for quantum numbers now since we're talking about that. So in other words, as you start moving along with the quantum numbers, you're going to have a whole bunch that are going to have that first quantum number the same. Then you'll have fewer that'll have the first and the second quantum number the same. When I get to my third quantum number, my magnetic quantum number, there'll be 2 electrons that at that point will have the same first, the same second, and the same third. And it has values of negative L to positive L, including 0. And remember, L was your angular momentum number. And then the last one that finally separates it to where you only have 1 electron with these is going to be your spin quantum number. And that's either going to be a positive half or that's going to be a negative half. And that's representing the opposite spins of the electrons within one orbital. So this one actually narrows it down to 1 electron. So I'm just going to go down a little bit where y'all have some space. I think y'all have some space here. And then kind of just show you what this is. I'm not going to test you on this, and you're not going to test on the AP. I would just like to show you what it looks like. So in case you see it in chemistry, maybe in college, if you have to take it, you'll know what they're talking about. So we said that F's, okay, they have an angular momentum number of 3. That's the number that's assigned them, 3. And we know F's can have 7. 1, 2, 3, 4, 5, 6, 7. They can have 7 orbitals. So if this is their angular number, then we said their magnetic number is from negative L through positive L. So what that means, if their number is 3, then this kind of becomes like a number line. You start in the middle orbital, that would be a 0, and then you go 1, 2, 3, and then on the other side you go -1, -2, -3. So if this was an S, all you would have is this 1. So that means it would only have a 0. So let's say that I am putting some electrons. Well, let's just fill these electrons up. And let's say that you were asked for the quantum number of this very last electron. So the first thing that you would have to know, which I don't have written down here, which you would have to be given, you'd have to know what energy level it was in. So let's say that that was energy level number 6, that you knew that. So that would be its first quantum number would be 6. Then because it's in an F, its second quantum number would be 3. Because it's in this particular order, its third quantum number would be -3. So you can see at that point, there's two that possibly can have these three numbers. So then it's the last number that separates them out. And since it went in their second, it would have a -1/2. So that would be show you what a set of quantum numbers would look like. They're not that hard. It's just kind of just dealing with them, but they're a little bit outdated. So you can see as you go more and more, it gets narrowed down until finally that last one, it has to either be a +1/2 if it was the first electron, or a -1/2 if it was the second one, and that finally separates it out. So maybe you'll get the pleasure of doing that in chemistry in college. I'm not really 100% sure on that. The second 3 came from, what did it, should have been a -3. Did I not write -3? Oh, the second 3, because all F's, if you go back up to right up there, at the top right there, see where it says 3 = F. Oh. That in quantum numbers, instead of using S, P, D, and F like we'll use in electric, they use those numbers. So any F would always be a 3. Any D would always be a 2. All right, enough of that for today. And I might ask you about quantum numbers, but I'm not going to ask you to figure out what a quantum number of an electron is. All right, so orbital shapes and energy. So this is more as we're moving into electron configuration. The reason we teach that is because it affects our periodic table trends. So regions have areas of high electron probability. Once again, that goes back to that Heisenberg uncertainty principle. And regions of 0 electron probability. And those are called nodes. So I am not at all a person that can really draw, but that would be an example of like what one of the p orbitals would look like. So this part in here, that would be considered the node, okay? So it's saying that electrons probably will exist here, electrons will probably exist over here, but they're not going to exist there in that middle. So that's what they mean by the node. So degenerate orbitals, there's just some vocabs as we go here. Degenerate orbitals are just orbitals that are equal in energy. So like if you're at a P sublevel, all 3 of those orbitals are going to be degenerate. If you're at an F, you would have 7 orbitals that would be degenerate, okay? That doesn't mean all P's. That I didn't make that very clear. If I was at a 2P, all of those would be degenerate. A 2P orbitals would not be degenerate orbitals with, let's say, like a 5P, because a 2P would be much lower energy. Then hopefully these 3 y'all remember a little bit. We talked about those. Pauli exclusion principle just says in a given atom, no 2 electrons can have the same set of 4 quantum numbers, which we talked about already, and then an orbital can only hold 2 electrons and they have to be in opposite spin. Aufbauer talks about that the electrons always go to the lowest energy first, and that's considered their ground state. And then that just gives you the order of filling, which is also what you have your periodic table tool to help you with. And then Huns Rule, also sometimes called the empty bus rule, just says that an orbital in a sublevel will have half filled with electrons before they start pairing up. Once again, you just have to remember these are negative electrons and they're trying to be kind of stuck together in a small area. So they're going to do whatever they can to decrease that repulsion. All right. Do a little electron configuration. Do y'all remember electron configuration, or did you go watch the video too? Remember it? All right. So this is going to be your little tool, just like I gave you. Don't forget that you got your 1S over here so it doesn't get lost. And I'm just going to put in these because we're going to use them. Oh, actually, I'm not going to put them in yet because I'm going to move them and they're going to get erased. So that's not really going to work. All right, so this is just your order of filling. Just remind you, you always start here and then you go across. When you get at the end of one, then you come back and start the next one. You do not go down, you go across. Thank you, sir. And once again, this is just a tool to help you with the filling because it tells you the order of which sublevels are the lowest to the highest energy. So with periodic table trends, they love exceptions. So kind of the two big exceptions are going to be chromium and copper. They are not the only exceptions, but they are kind of the two big exceptions. So if we look at copper, its electron configuration, I'm going to do the noble gas notation because that's nice and short. Its notation, we think it should be argon and then 4s2, 3d9. If you look at, which one am I doing? If you look at copper, it's element number 29 on the periodic table. So if you count in, that's 9 into the 3D. So this is what we think it should be. And then what it actually is AR 4s1 3d10. So one of those electrons goes from the S to the D. And we're going to have something pretty similar with chromium. We think it should be AR 4s2 3d4. But instead it is, as I'm sure you can pretty well guess, it is actually 4s1 3d5. And the reason this is the S sublevel is smaller than the D sublevel. So there's a lot of electron-electron repulsion when both of those electrons are in the S. So even though the S is a little higher in energy, it still is worth that energy to jump that electron up to the D. So moving that electron decreases electron repulsion. In the smaller S sublevel. Remember, everything wants to be at the lowest energy possible or lowest potential energy. So even though it's jumping that electron up a little bit more, it's worth it to get out of that electron-electron repulsion that it's feeling. So those are kind of the big two. There's some other ones that kind of go in 3D, and then the exceptions start to increase even more as you go to the different energy levels. And the reason that is, as I go down the different energy levels, the S's are farther out from the nucleus. So decreasing that electron repulsion has a big energy payoff. It's worth them for them to get it out of an S and move it into a D. All right. So orbital notation or orbital diagrams, just to kind of refresh your memory on what those are. My little notes there. All right, so the orbital diagram is when you show your orbitals and then your electrons are represented with the arrows. We did those. We didn't usually do boxes. We usually just did our different lines. So this would be like a 1s and it could hold 2 electrons. And then you would go through your next thing, which is your 2s. And then if you did a P, you would draw 3 lines. And remember, you put 1 in each before you double up. So that's just an example. That is your orbital diagram that includes all of that. Then our complete electron configuration is when you write all of that part with superscripts to represent the electrons, but you leave out the lines and the arrows. So if I took this, it would become 1s2, 2s2, 2p6. So what element would I be representing with that electron configuration? It's neon, exactly. Remember, if you add up your superscripts, that should tell you how many electrons you have. And then your noble gases, because they're your very last one, they should all be ending with some energy level P6. It should be completely full. The noble gas is probably the one that you'll see the most on the actual AP test because it shortens everything. So if you remember, your noble gas one is when you use the noble gas that is before the element to represent a large portion of the electron, of the periodic table. And then you write just what you need in that period to get to your element that you're looking at. You cannot, and I don't know why, because this isn't my rule, you cannot use a noble gas for itself. So in other words, if I was talking about neon and I wanted to write the noble gas notation of neon, it seems to me that I should just be able to put neon in the brackets. Makes sense, but you can't. You have to go up to the one before. So you'd have to go up to helium and then write all that part. Okay, so this would be an example. We got phosphorus right there, which is element number 15 on the periodic table. So I would go to the noble gas before it, which would be neon, not the noble gas after it, but the noble gas before it, neon. That represents neon and everything before it. And then I would just need to write what I needed in the period to get to phosphorus. So that's where that 3s2, 3p6 comes from. Yes, no, y'all remember all that good stuff? All right, ions and electron configuration. Remember that ions are either usually gaining or losing electrons so they can get a noble gas notation, because that's where they're going to get stability, a full valence, okay? So we know ions are charged particles that are formed from atoms by the loss or gain of electrons, and they do this to become more stable by decreasing their potential energy. So we know our group 1 metals are our most reactive metals. They only have 1 electron in their valence shell. So if they can get rid of that 1 electron, they can fall down to a next energy level, which would be full. And then that would be much more stable for them. The magnitude of the charge, whether it's either positive or negative, is going to denote how many electrons are either going to be lost or gained. So just to refresh your memory, if it's a positive ion, that comes from those are called cations, or some people call them cations. I think of the T as a positive. That helps them remember they're positive. And these are the ones that are going to lose electrons to become positive, because remember they're losing something negative. And that's usually what our metals do. And then we could switch that all around. We would say if we have a negative ion, those are called anions, which means they have gained electrons. And this is what the non-metals do. Also, if you look at your polyatomic list, sometimes most of the polyatomics that we deal with or that are there are negative. We have a lot more negative anions than positive as far as our polyatomics go. All right. And then your, because we'll use this in a little bit, your valence electrons are represented by the outermost or highest energy level S and P orbitals. So if I have some kind of transition metal that's in the Ds, that's not your highest energy level because they're always running one behind your S's. So those valence electrons are lost out of the S. They're not going to be lost out of the D, lost out of the S or the P, depending on what element that we're looking at. All right, so some electron configurations. We've already talked about copper because it was an exception. So cobalt, we'll do CO is cobalt. I don't think I need to do all of these, but cobalt is element number 27. So if I'm doing my noble gas or short notation, what noble gas am I using? Argon, exactly. So I'm putting argon in brackets. So that takes care of argon, which is number 18. That takes care of it and everything above that. So that means cobalt is in period number 4. So I just need to write what is in period number 4. So that's going to be my 4s2 and then my 3d7 will get me to cobalt. Oh, no, that should be down here for cobalt. Sorry. We'd already done cobalt. Yeah, we'd already done that one. All right, so I'm not going to go over all of those. Y'all will have some on practice. If you get home and you have some questions, and we can come back and do that. I don't want to waste y'all's time or already feel like some of y'all are falling asleep on me on a Friday. All right, so these are our ions. So just remember that all that means is that their electron configuration is going to change. It's either going to have one more electron added to it if it's negative, or it's going to have electrons taken away from it if it's positive, okay? So if I look at fluorine becoming fluoride, I'm going to write fluorine first. This is actually not going to, this is going to be fluorine. It's 2p5. This is fluorine, the atom without a charge. Okay, you can see this 2p5, that's 5. So if I look at the valence, I have 2 here and I have 1 here. So 7 valence electrons, 1 less than 8, making it very reactive. So it becomes an ion, it becomes a -1. It gains an electron into there. So it just becomes 1s2, 2s2, 2p6. That is your fluoride. And but the difference between fluorine and fluoride is one is neutral and one is now an ion. So, and this is isoelectric with neon. Isoelectric means it has the same electron configuration. So all of these, I'm not going to go through and do all of these. We can do a positive one if you want to, but all of them, when they either gain or lose electrons and become ions, they are going to become isoelectric with some type of noble gas, because that's the whole reason they're doing it. In that process, they also become isoelectric with each other sometimes, but the reason they're doing that is because they want to have that stable electron configuration. All right, I'm just going to do a positive one real quick if you need it. So once again, I'm going to do what it should be, so or what it is as it changes. So I'm going to do, this is aluminum to start off with, 2s2. Oh no, I didn't do it. What is aluminum? Then it is what? Oh, I did it after I'd already changed it. Let me regroup, y'all. So aluminum as it is Ne, and then 3, 2, P1. Okay, so right now valence, because remember that's your outermost S and P. Right now it has 3 valence electrons, making it not horribly reactive, but well, not real reactive, but it would still like to have noble gas notation. So it's going to get rid of all 3 of those electrons. That's because why it becomes a +3. And when it does that, then it will have the noble gas notation. It'll have the isoelectric notation of neon. So we'll change its noble gas notation to helium, 2s2, 2p6. So this makes it isoelectric with neon. This is aluminum, which I usually can't spell, and this is definitely didn't spell right there. I did spell right the first time. The other thing that I usually spell wrong is also fluorine and fluoride. I usually leave the U out on that. All right, questions on that? Do a little practice on that. If you're having problems, we can go over it if we need to. Definitely try some transition metals because they're not going to be losing or gaining electrons out of that. They're going to be out of their S or P. Polyelectric electronic atoms with more than one electron. So that's anything behind after hydrogen. I'm not for sure why we really need a whole little vocab word for that, but anyway. Okay, next page. Y'all read over that at home. It's mainly vocabs. And we'll just hit them real quick and move on to periodic table trends. And that's where the fun starts, especially on that next page with all those definitions. Please especially pay close attention to the first two, the first paragraph and then shielding, because that becomes a big deal about periodic table trends. If you hadn't watched the video, then take some time to watch it. I put one in there today that goes over periodic table trends over the weekend. If you have a little extra time, try to watch that to give yourself a head start. Usually